So we've now had an opportunity to look at gases, liquids, and solids, different states of matter, how they hold on to one another, and basically what keeps them together and some of their properties. What we're going to do in this unit is we're going to look at solutions, and solutions aren't their own unique state of matter because, again, a solution is going to be a mixture. But we do want to take a moment in this unit to look at a couple of things. Number one, what is it that causes a solute to dissolve in a solvent, right? Why does that happen? What are some of the energies involved in that dissolution? And then we're also going to look at, as we see in this episode, we're going to review how to come up with different ways of describing the concentration of a solution. And finally, we're going to be looking at what properties of the original liquid or the original solvent get altered when we introduce a solute into a solution. So there's a lot of extra neat little stuff that comes in with solutions, and we're going to use this unit to kind of dive into each of those individual concepts. We're starting off with, first and foremost, how do we determine the concentration of a solution, not just from what we learned already using molarity, but how do we use things like parts per million, percent by mass, maybe percent by volume, and of course we're going to be looking at the cousin of molarity, molality. So as we learned earlier in the year, when we talk about concentrations of solutions, we're often going to have to distinguish my solution by describing the solute, the thing that was dissolved, and the solvent, the thing that is doing the dissolving. Now, when we first looked at aqueous solutions, basically solutions where a solute, a solid, basically broke up in water, right, to keep it simple, we looked at the first form of measuring concentration, which is the most common and popularly used in chemistry, this idea of molarity. And again, just as a review, molarity is nothing more than moles of solid divided by liters of solution. Now, one of the things to recall, I do not see molarity as an equation. I see this very much as a ratio. It's a relationship between amount of solute and the total volume of solution, right? So everything put together is the denominator. Now, there's another one that we have special circumstances where we use it, and this is known as molality. Just so you're aware, if we usually abbreviate molarity with a capital M, so molarity is usually going to be big M like this, molality often is going to be seen as little m. It'll look like a meter. It's not, it's molality. Now, molality is different from molarity because in molality we are going to differentiate. We're going to separate my solute on one hand and the solvent, the thing doing the dissolving, on the other. Now again, the ratio, the relationship is moles of my solute divided by kilograms or mass of my solvent. And, oftentimes students will ask, well, why do we need two? Isn't molarity work in most instances? And the answer is yes. Like I said, the biggest distinction between the two of them is that molality is going to differentiate, it's going to splice apart your moles of solute and your solvent. And that comes in handy when we're looking at certain properties of a solution. There's something known as colligative properties. We'll touch that later on. But when you look at properties of a solution, we oftentimes have to kind of like figure out, well, what did the solute do? What did the solvent do? And in those instances, molality will become important. Now, another very common way of measuring the concentration of solution, especially when you're doing things like you're looking at a water supply, you're looking at, let's say you're reading the back of a label of something, and it might say something like there's so many parts per million or parts per billion of a substance in this solution. What we're really doing is we're looking at this idea of mass percentage, right? So what is the percentage by mass of a part, usually the thing in question, right? So the solute, quote unquote, the thing maybe we're looking for. So if we're measuring like lead in a water supply, it'd be lead ion. If we were measuring mercury in a water supply, it'd be mercury ion, right? So what is the mass percent? What is the mass of the portion divided by the total mass of the whole? Okay, so mass of a portion on top divided by mass of a whole below. Now, what happens when we're talking about infinitesimally small quantities. Well, in a case like that, then we use this idea of parts per million, ppms, or ppb, parts per billion. And everyone loses their mind when we start talking about parts per million and parts per billion. So let me help you. A mass percentage by definition is of 100. So when we're doing mass percentage, all we're saying is we're basically taking the mass of the part divided by the mass of the whole, and then we're going to multiply by 100. And this is going to give me a percentage of 100. But if I have teeny tiny amounts, then instead of multiplying by 100, I might multiply by 1,000,000. And when I multiply by 1,000,000, now I'm talking in terms of parts per million. If I multiply by 1,000,000,000, 1,000,000,000, then that's going to be parts per billion, right? But at all times, when we talk about mass percentage, we're talking about a part over the whole. Now, the same way that this could be a mass percentage, sometimes this could be a percent by volume. So maybe you've gone to like the drugstore before and you've picked up some rubbing alcohol and it'll say like 5% rubbing alcohol by volume, or 3%, maybe 3% hydrogen peroxide by volume. It's still the same idea. The difference is, what are we going to be measuring? Are we measuring volumes or are we measuring masses, right? It's still mass of the part divided by mass of the whole, or volume of the part divided by volume of the whole. So because these types of questions can sometimes throw students, let's take a second to practice how to come up with something like parts per million. So take a moment, go ahead and pause this, write this question down, and let's jump right in. A 3.50 gram sample of water was found to have 6.5 micrograms of calcium ion in it. So again, 6.5 micrograms is nothing. It's a drop in the bucket, right? But we want to know, what is the concentration of calcium ion in parts per million? Meaning, for every million particles of solution, how many are going to be Ca2 plus? Now, my guess is however many are Ca2 plus, the rest of those million, the 999 whatever, are going to be water. But what we're going to do in this case is we're going to start, once again, by measuring a part and dividing it by the whole. We know that the mass of calcium was going to be 6.5 times 10 to the negative 6 grams. That was its mass of the part. We divide that by the total mass of the solution. In this case, it's going to be the water plus whatever else was in there. And when we do that, we're going to get an itty bitty number. But to help us, we then multiply that number by the million. And when we multiply by the million, we get an answer that's going to be 1.86. Now, 1.86%? No, 1.86 parts per million. Now, to get an idea of a bit more challenging problem, what we can now do is we can now take a look at your typical, let's say, beer can or beer bottle. A beer bottle says that it contains 5% alcohol by volume. What is the molarity? Notice I'm asking now, let's go take it back to how we normally and typically think of concentrations, right? What is the molarity of ethanol, C2H5OH, in a typical 12 ounce, which is roughly 0.355 liter bottle of beer? Now, the density of ethanol is usually in around 25 degrees Celsius. As density of ethanol in water or solution of it is going to be 0.789 grams per milliliter, okay? So, again, take a moment, write the question down. And let's go ahead and start tackling this problem as well, because this is not what I would consider to be a hard problem, but it's one of those problems that students often struggle with because they don't really get, well, what do I do? Where am I going? What can I really use here? So look, at the end of the day, the beer bottle has 5% alcohol by volume. We get it, that's not a lot. But how do I make that into a concentration, into a molarity? And that's where it can get a little bit tricky. So let's look at the steps. We're going to start by taking the original volume of my beer bottle. So the original volume is going to be 0.355 liters, right? Now that's 0.355 liters in total. That's the whole solution that contains the ethanol and the water and anything else that might be in there. So the first thing I'm going to do is I'm going to go ahead and convert that into milliliters, because here's what I know. When my percent by volume is 5%, right? Again, let's think this through. Percent of 100. That means for every 100 milliliters of quote-unquote beer, right, 100 milliliters of it, only 5 milliliters are going to be ethanol. So you see this 5 over 100? This represents my 5% alcohol by mass. So what I've done is I basically asked the question, of my original volume, of those original 0.355 liters, how much volume is ethanol? And that takes me this far into the problem. So now I go ahead and say, well, now that I have a volume of it, I have the density. So if I go ahead and I see that density is nothing more than a way to compare volume to mass, I know that I have 0.789 grams of ethanol for every 1 milliliter. This now gives me grams of ethanol. I can convert my grams into moles of ethanol. I know for every 1 mole of ethanol, I have 46 grams. Now at this point here, I'm now left just with moles of ethanol. So I'm almost there. I didn't want moles, I wanted a volume. So excuse me, I wanted a concentration. So the last step is I'm going to go ahead and now take my moles and I'm going to divide it by what was the original volume of the solution. And the original solution had a total volume of 0.355 liters. So when I do all of that, I'm going to get a concentration of 0.857 molar, or 0.857 moles per liter. And again, this is a good example of how you should be able to move from one form of concentration measurement into another form and not be terrified. It's really not that scary. And so finally, the last way that you might be asked to determine the concentration of a solution is you may be asked, and this again we'll see later on when we start talking about molality and we start looking at the properties of a solution, but you may be asked to determine the mole fraction, right? Now again, mole fraction is nothing scary because mole fraction basically represents kind of what the name implies. It's what is the fraction of the part one substance compared to the total amount of substances. So let us say, for example, that I wanted to know the mole fraction of A inside of a container that had A, B, and C floating around in it. So what I would do is I would sit there and say the mole fraction of A is going to be however many moles of A I have divided by the number of moles of A plus B plus C. So I add all of those up, that gives me the sum or the total number of moles, and then I produce a value less than 1, or a fraction of how much A brings to the total number of moles. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.